In part 2 of the Unit 1 notes, we will be covering precision versus accuracy and calculating percent error. Precision is a measure of how close experimental values are to one another, whereas accuracy is a measure of how close experimental values are to an accepted value. These two words are often used interchangeably, but they do not mean the same thing. An experimental value is the value that is measured during an experiment. If we were to do a lab in class, these would be the values that you're actually measuring. The accepted value is the correct value based on a reliable reference material. These could be the values for, say, a density that you might find in a textbook or some other reference chart. You can consider a measurement precise or accurate if values are the same in the ones place and only off within the tenths or hundredths place. This is a generalization that we will be using for our class based on the scale that we will typically see. If you wanted to, you could also calculate a percentage error based on the precision and accuracy, but it won't be necessary for the numbers we'll be using. In this example, we are looking at the data collected by 4 lab groups for the density of lead during a chemistry lab. The recorded experimental values are shown in the table below. The accepted value for the density of lead is 11.3 grams per centimeter cubed. So we could say that this is the correct value. Now we have our 4 groups here. So group A believed that it was 9.0, group B was 9.3, group C was 9.5, and group D was 9.2. All 4 sets of data are very close to each other. They're all the same within the ones place, and they're only off within the tenths. So we could say that this data is precise. But this data is not particularly close to the actual accepted value of 11.3. So it would not be considered accurate. If we wanted to show this in a picture form, you could look at this target right here. So all of our values are very close together, but they are not hitting the bullseye. Example 2, this is very similar. So we still have 4 lab groups. They're calculating the density of lead. This time we have 5.0, 7.1, 10.5, and 2.2. So now our data points are really spread out. They're not particularly close together, and they're also not close to the accepted value. So we would say that this data is definitely not precise. It's off by too much, and it is also too far away from the accepted value, so it is not accurate. For example 3, our groups have collected data again, so we have 11.0, 11.3, 11.5, and 11.2. This time, not only are all of our data points very close together, they're only off within the tenths place, they are also all very close to the accepted value. So in this situation, we would say that the data is both precise and accurate. Next, we will be learning how to calculate percent error. The error is the difference between the experimental and accepted values. The error can be calculated with subtraction. The sign of the error represents whether the experimental value was higher or lower than the accepted value. But when we actually calculate percent error, we are going to be using the absolute value, so the sign is not actually going to matter. Percent error expresses error as a percentage of the accepted value. The percent error can be calculated by taking the absolute value of the error and dividing it by the accepted value multiplied by 100. So this is the equation that we are going to be using right here. Experimental value would be whatever you are actually determining within the lab. The accepted value is what you're getting from some kind of reference material, and then we are also dividing by the accepted value. So here's an example of a type of calculating percent error problem that you might see on a test or a quiz. Remember that for all checkpoint questions, you should be writing out the solutions to these in your notebook. A high school chemistry student measures the mass and volume of a piece of aluminum and uses that data to calculate the density. Their experimental value for the density of aluminum is 2.45 grams per centimeter cubed. So this is going to be our experimental value. Calculate the percent error if the accepted value is 2.70 grams per centimeter cubed. So we have percent error And first thing we have to write out is our experimental value, which is 2.45 grams per centimeter cubed. We're going to subtract the 2.70 grams per centimeter cubed. And then we would divide by the 2.70 centimeters cubed, grams per centimeter cubed. As far as order of operations is concerned, you should be subtracting up top first before you divide on the bottom. And I almost forgot, we do have to multiply by 100% as well in order to turn it into a percentage. So when you multiply across here, we end up with 9.26%. Again, when you plug this into your calculator, you would actually get negative 9.26, but because the sign doesn't matter here with the absolute value, your final answer for these percentages will always be positive. All right, we have one more similar checkpoint solution. So this time it looks like our experimental value, we're looking at the density of sucrose, is 1.54 grams per centimeter cubed. And the accepted value is 1.59 grams per centimeter cubed. So we have our percent error. Our experimental was 1.54 grams per centimeter cubed. We are subtracting away our accepted value. We're going to take the absolute value of that, so the sign is not going to matter. And then we are going to divide by the accepted value, which was 1.59 grams per centimeter cubed. When we plug all that in, we end up with 3.14%. Now for percent error, if you are fairly close to the accepted value, you will want your percentage to be very small, which is what we saw in these two examples. 3.14% is a very low percentage of error. If your percent error was, say, around 90 or 100%, that means you were really far off in your data. That concludes part 2 of our Unit 1 notes. When we come back for part 3, we're going to be going over the calculation of volume for a regular object, calculating the volume of an irregular object, and calculating density.